We're going to take another look at inverse functions. Now, an inverse function is when there is a one-to-one relationship between the two sets of domain and range of a function. If it is a one-to-one relationship, then we know that both the relation and its inverse relation are both functions. And in that situation, we don't call it an inverse relation, but we call it an inverse function. Now, a function is either going to be one-to-one or many-to-one. If it does turn out to be one-to-one, then we know it has an inverse function. And the composite function of a function and its inverse will always turn out to be x. So if you substitute the inverse function into the function, you should get x. If you substitute the function into the inverse function, you should get x. Now, how do you test for inverse functions? A horizontal line test. You remember we used a vertical line test to see if it was a function. The horizontal line test, so that's if it cuts it no more than once, then that will tell you if that function has an inverse function. So that's how you visually can tell. So the algebraic way of doing it is if you swap the x and the y's around, so you get x equals function y, but you make y the subject of that. Now if you get something that's unique, so you don't find yourself saying something like plus or minus, then it is an inverse function. Now the inverse function of an odd function will always be odd, whereas even functions will not have inverse functions, because even functions have symmetry in the y-axis, so it will fail the horizontal line test. Okay, domain and range then. So if AB is a point on the original function, then BA, so swap the x and the y's around, BA must be a point on the inverse function. So what that therefore means is the domain of the original function will become the range of the inverse, and the range of the original function will become the domain of the inverse. So let's start with a simple little example. Our exponential curve. So y equals e to the power of x. Now we know the domain of that is all real x, and we know the range is y is greater than 0. Okay, so if we want to find its inverse, swap the x and the y's around, so x equals e to the power of y equals log x. Now it will be an inverse function, because if you look at the original function, yes, it satisfies the horizontal line test. The inverse is log x. So its domain should now be x is greater than 0, because the range of the exponential was y is greater than 0. And the range of our new function, log x, should be all real y, because the domain of the exponential was all real x. Now when we draw it in, what we should find, if we put them on the same axes, that the curves are reflections of each other in the line y equals x. So there we go, we put them on the same one, and you'll notice that the y-axis acts like a mirror, if you like. Most functions won't have an inverse. The only ones that are going to have an inverse are curves that are continually increasing or continually decreasing. So you sometimes have to restrict the domain, get a piece of the function that would be one-to-one, a piece of the function that would satisfy the horizontal line test. So we want that piece of the graph that's continually increasing or continually decreasing. So let's have a look at the parabola y equals x squared. Now it fails the horizontal line test, so we know it's not going to have an inverse function. The domain at this stage is all real x. The range is y is greater than or equal to 0. But as I say, no inverse because it fails that horizontal line test. We want to restrict it. So we want to grab a piece of that parabola, which is always continually increasing or continually decreasing. We actually have a choice there. If I choose the left side of the y-axis, then the parabola is continually decreasing. If I choose the right side of the y-axis, then the parabola is continually increasing. Now usually we'll go with the positive. So I'm going to restrict my domain to be x is greater than or equal to 0. The range, if I just look at that piece, is still y is greater than or equal to 0. That hasn't changed. So that's the other thing we want to try and do. We want to capture as much of the range as possible. In this case, we were able to get all of it. So what is that inverse going to be? Well, swap the x and the y's around. So x equals y squared. Make y the subject. We get y equals x to the power of a half. Or in other words, the square root of x. Its domain is x is greater than or equal to 0, and its range is y is greater than or equal to 0. If we draw it in, it's our sideways parabola, but just the top half. And again, if you look in the line y equals x, you'll see they reflect in that particular line. Here's one from an HSC, the 2010 paper. So function is e to the minus x squared, and they've drawn the graph for us. They've told us it has 2 points of inflection. Now, points of inflection, that's where the curve changes concavity. We want to find the x-coordinates of those particular points. Now, one of the things we'll see when we look at calculus a little bit further, inflection points will always happen when the second derivative is equal to 0. So let's differentiate. Function x is e to the minus x squared. Differentiate the exponential. Differentiate the power, that's minus 2x. So minus 2x e to the minus x squared becomes our derivative. Now we'll find the second derivative, but I have to use the product rule. Write down the first, minus 2x. Diff the second, well, that's minus 2x e to the minus x squared. Plus, write down the second, e to the minus x squared. Diff the first, negative 2. Got a common factor of e to the minus x squared, and inside the parentheses we get 4x squared minus 2. We're saying, when does that equal to 0? Well, either the exponential equals 0, that can never happen, or 4x squared minus 2 equals 0. And that'll be when x equals plus or minus 1 on root 2. Now, normally we would go and test those points, because these are just finding possibilities for the inflection point. But since they have told us it only has 2 points of inflection, and we've found only 2 answers, they must be the inflection points. Explain why the domain of function x must be restricted. That's to get a piece of the curve that's continually decreasing or continually increasing. The fancy way of saying it here is, in order to have the inverse, there must be a one-to-one relationship. Find a formula for the inverse. Okay, swap the x and the y's around. So if x is now equal to e to the minus y squared, we want to make y the subject. Bit of playing around, we eventually get y is plus or minus the square root of log of 1 on x. But I just said plus or minus. So that's not an inverse, because we got the 2 possible answers, plus or minus. Which one is it? Well, we know the domain of the original curve becomes the range of the inverse. So if the domain of the original one was x is greater than or equal to 0, the range of the new one must be y is greater than or equal to 0. Therefore, it must be the positive square root is what we're looking for. So y equals the positive square root of the log of 1 on x. So what would the domain of the inverse function be? Well, the range of the original function becomes the domain of the inverse. So looking at the original curve, the range was in between 0 and 1, but not including 0. It went asymptotic to the x-axis. So therefore, the domain of the inverse will become x is in between 0 and 1, but not including 0. And then they want us to give a sketch. And there's my sketch. It's a reflection in the line y equals x. Okay, so 17a, bit of a recap on inverse functions.